Hello and welcome back to another LeetCode problem. So today we're going to be doing problem number 212, word search 2. So we're given an m by n board of characters and a list of strings, and we need to return all words on the board. Each word must be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring, and the same letter cell may not be used more than once in a word. So we're given something like this, we're given a board, we're given a list of words, and we need to construct this. And so it's going to be difficult to do some kind of DFS or something because the length of this word list is very long. But this is n by m, where n and m are very short. I think they're like 12 only 12 spaces long. So when you see something like that, when you have a huge word list and a short board, so you are probably going to have to do some kind of search, but something like a depth first search makes a lot of sense with backtracking. And the reason we can use backtracking is in order to store indices we visited earlier, like let's say we start at this O. In order to store indices we visited earlier, it really matters where we got there from. So for example, if we get here, it really matters where we got there from. Like, did we get here from this O? And if we did get here from this O, did we originate at this O, or did we maybe start here and then go to here and here? And so when there's all these different combinations, and just because you get to an index doesn't mean all these iterations are different. It really matters where you got there. You're going to have to do something like backtracking as opposed to memoization, because all these different things can't really be recorded. Like, you'd have to record the exact path, and then you're storing entire arrays, which is not great. So whenever you have an array of a path, you typically want to use backtracking instead. And so the other thing is, when we traverse, how do we really know if we get a word? Well, one thing we could do is we could have a path, and then every time we get to a letter, so let's say we go this way. So we have oath, right? We could be like, okay, we have oath. Is oath in our dictionary? We have some other things that are in our dictionary. But that's going to get expensive rather fast because this words is really big. So is there a better way to know if this is in our dictionary or if this is in our words without traversing it every time? And there is actually a better way to do that. And the better way to do that, when our words list is long, but all the words are kind of small, and we have this small board, is using a try. And so the basic concept of a try is it's going to be a path. So let me just demonstrate. So it's going to be a variable. Let's just say this is the try. And it's going to contain every letter in it, and then every letter is going to point to another try. So for example, for oath, we're going to have a root. So this is going to be the root instance variable of the try. Then it's going to have every single try is going to have a dictionary of children with keys being a letter, and then the value being another try. So like this is the root, let's say. Now we go to O, we get to another try. This O has an A, right? Get to another try. This A has a T. Get to another try, and then an H here. And then also if tries share the same letter, so for example, this root can have an O, and then this can point to, like, let's say of, if of was a word or something like that. So we're going to, whatever node we start at, we're going to start at the root. We're going to traverse down every time, and we're going to ask ourselves, so the other thing a try has that's kind of important is every time we traverse down a letter, so there would be actually a try here at the end, try here at the end, we would say, okay, once we're at a try, all we have to do is we can have a variable, a boolean for the variable called, like, let's say we call it end. And if end is true, that means we've reached the end of a word. And so we can iterate through this words dictionary one time, take all of these words and make a try. So for example, let's see what a try would look like for all of these words. So starting with oath, right? So let's delete this, and let's do that. So we start with oath. Remember, we have this root node, so let's just call that root node. We go through an O, go to another try, go to an A, so go to another try, T, another try, H, another try. Now we've reached the end of the word, so we're going to mark this equal. We're going to say this is an end, and I'm just going to make this red, and red means the end of a word. So we also have P. So P is a completely different, it doesn't have any of the same letters. So this dictionary, once we're at this try, this will have a dictionary of every single letter that we used words for. So it would add this P, and then E, and A. Have another try down here, same thing. This is showing that we reached the end. Now we have rain, or we have eat, sorry. So eat is completely different as well. So E, A, we're not sharing the first letter. And then this is another try, the end of the word. And finally rain. So rain doesn't share anything either. So R, A, I, N. Okay, and this is this. And so when we traverse down, like let's say we're at oath, so we start at the root, we go to O, then we go to A, then we go to T, then we go to H, and we see, oh, we're at this end node. That means this is a valid word. And we're just going to keep track of the current word. Like we're just going to have some kind of current array that's going to keep track of every single letter that's in our path. And as soon as we hit an end node, we're going to add whatever current is to our result. But keep in mind, we can't just go back as soon as this happens, because there might be a longer word that contains this word. So for example, this oath might also contain a word like oaths. So even though there's an end, we have to keep going until we backtrack fully. So you could see like this would be a word as well. So we don't, our return condition wouldn't be if we just hit a word, we'd have to keep going. But we can have a return condition where we are at some try, and we can see, okay, does this try have any paths from it? Does this have any letters in it? If not, we don't really need to keep going because there's nothing in here, so we can just return there. So that would be an end condition, as well as if we check every single index in a backtrack. And also keep in mind for these tries, words can share letters, right? So let's say this is a root, so we have E, but we might have ears maybe. Could be a word. So then it would go down the same path. So it would go to EA, but then it would go here into this try, and this would be an end node. So that's kind of how tries are represented. We're going to have a dictionary of letters as keys, and then they're going to point to other tries. We're going to start at a root, and we're going to traverse down, and we're going to use this end variable to know that we have a result. And we need to start at every single node in this grid, and we need to try to traverse in every direction using backtracking. So by the way, so we can look at also, so this is going to give you a lot of hints to do things like that. When you see this M is really small, this N is really small, that means backtracking is going to be something useful. Because if let's say this grid was like 1,000 by 1,000, then if you backtrack, that's going to get really expensive. And also you see this word length is really big, so you don't really want to compare every single node you're at to the words like, where if this word length was only like 10 words, then we could easily just compare every time instead of using a try because it's kind of small. Okay. So hopefully that makes sense. And let's just start coding it up. So first of all, we're going to have a try class, right? And the try is going to have, so actually for our try, I don't think we need to pass anything to it. So we're just going to have an init try, and then we need self.children equals this empty dictionary, right? And self.end equals false. We can give our try a character, but technically we don't need to do that because these should all be connected. So then we need to go through this list words, and we need to make this list of tries. So this would actually not be a try. This would be a try node. Okay. So now the try is, the actual try is this full tree type looking thing, but all of these are actually try nodes. Okay. And so first we need to make a root, and that's going to be our root node that we're just going to start at, and then we're going to keep starting at the root node and go down all of these words to make our actual try. So we can just say root equals try node like that. It doesn't take any values, so now we just have to iterate through every single word. So for a word, words, and then we have to iterate through every single character as well. So for char in word, so for word and words, first we have to start at the root, so we can do something like this, cur equals root, and then we are going to traverse down every single character. So if char in cur dot children, yeah. If so, it's actually if not. So for example, when we don't have these children, we need to make them, right? So when we start with our initial root, like we start with our root, and we're going down some word like word, when we're at this root, we check the children, the W isn't in there, so now we need to make it. So every time the character isn't in the children, we need to add it in, and then we need to go to it. So if character not in cur.children, then we add it in there, right? And so we do cur.children char, and then we create a new try node. And then now we just simply traverse because we would have made it where it's already in there. So cur equals cur.children char. Then once we traverse that whole word, so now we're going to be at the try node that's the end of the word, and now we need to make this end true. So just cur.end equals true. Okay, so now we made all of our tries, and now we need to use this DFS backtracking algorithm to actually search for all these nodes. So first we're going to want a couple things. We're going to want some kind of sort of backtracking. It's good to have a cur array and a res array, right, for the actual output. So we can just have res equals this, and then cur equals this. And then our cur is actually going to be a list of characters, and then we're just going to join those together and put it in the res once we actually have a word. Okay, so def DFS, and the DFS is going to take an index, and it needs to take a node because we need to see what try node are we in, I believe. So we're going to pass in the root to start off, so it's just going to be a node. Okay, so like I said, if the node we're in has no children, right, that means that we can't go anywhere, so we can just return straight away. So if node.children, I guess we can just say like this, if not node.children, we do need to actually check if we're at this node. We do need to still check if it hasn't. So like if we're at an end node, even though this node has no children, we're still at an end node, so we would have to append that word. So that's the first thing we can do. So if node.end, that means it's true. We do need to append this cur, so we just need to do res.append, and then we need to join cur, right? So join cur. Okay. So now we do that, but then we need to keep going because this can have more children. So if not node.children, we can return here, I believe. Now, what are our other cases? Well, if we have children, we need to actually DFS into all of these letters. And so what we would do is, let's think. So the way we would do this is we would get, another thing we can do is we can add this directions array. This is always useful for DFS. So directions equals like this, 0, 1, -1, 0, 0, -1. Okay. So let's say we're here. If we try to DFS into one of these, we can only DFS into one of these if it's actually in the children. So if it's not in the children, we don't need to DFS it. For example, if we're at this 0 and A is not in the children, then we don't have to go there. So the only way we would have to DFS is if it's a valid index and if it's also in the node's children. By the way, so this index should actually be a row column. And so another thing we can have here is this as well. Equals length board and length board 0. This is good to have for checking if we're inbound and things like that. Okay. So we need to check all these directions and get new directions. Let's do that. So for, let's just say direction in directions, new row, new column equals row plus direction 0 and column. Okay. Now we need to check if they're in bounds. So if new row is, so we need to check if everything's in bounds and it's a valid, and there's something there. So new row is this less than rows and 0 this new column less than columns. And so remember, we need to check if this letter is actually in our children. So if board new row new column in, and then this would be node dot children. Okay, so now we have everything valid, I believe. Now we can backtrack to it. And so we would say, we would just call DFS on that. So we would say something like DFS new row new column. And then this node would be node dot children. And then it would be this letter right here, right? So that's what we would pass in. I think that makes sense. Otherwise, we don't even have to DFS into it. Okay, and now let's think about, do we even need a return value? I don't think so. I think once we go through all these backtracks, we're not really modifying anything. We're just updating where to go from here, which I think is fine. Okay. So I think that looks good. So let's try to just see what that looks like and see if we have any issues. Oh, by the way, did we need to add to cur and remove from cur and things like that? That's another thing we would need to do actually. Yeah, so actually we do need to do something. So if this is a valid location, how do we do this? So I think actually instead of checking this, let's think about this. So we're at a root. We're going to pass something. No, I think this is fine actually. So what we do need to do is we do need to actually add it to the cur here, I believe. Do we need to do that here? No, I think we're going to do that here. Yeah, we're going to do that here. So it's going to be right over here. We need to add that here. So cur dot append board row column. That way, yeah, so we get to, so let's say we're at this O, we check, is this A in our O? Yes, it is. So then we go to A, and then we need to append here. And then what we are going to do when we loop is, we don't need to go to, I mean, we could have a check here as well for that actually. But no, I don't think that would make sense. Well, so what we're gonna have to do in our loop is we're gonna start with our root. We're gonna start with our root node, and we're gonna check, is this letter, are all these letters in our root node, and if they are, then go there. If not, we don't even have to start there. So for example, if we look at our picture, right? Let's say for this one, our starting letters are E, P, O, R. So then any letter that's not in, like once we traverse this whole thing, if it's not E, P, O, R, it's not going to be a valid start index. So we can skip all those. Okay, so let's just double check this code just to make sense. So we have directions, we have rows, we have this. This should be fine. Res cur. So once we're at an index, we need to append to the cur. Okay, makes sense. So the other thing we need to do as well is, because this is a backtracking, I think right before we return, we're going to need to delete what we appended here. So we can just pop to delete. And I think that makes sense. So like, let's say we're here, we go to A, we append, but then we return, we pop. Okay, I think that makes sense to me. If node.end, that looks good. That looks okay. So let's just try this code and see what kind of bugs we're into. Oh, by the way, so we do need one other thing. So we are going to do this nested loop where we loop through this whole matrix, and we check if we can do these. So let's do that. So for row in range rows, for column range columns. So remember, we need to check if this value is actually in the children of the root node. So if board row column in, and then where's our root node, right? So it's going to be root dot children. Yes. Then we can just pass it in with the root, I believe. Yes. And then in this DFS, we're going to, we're going to pass in this next thing. So we actually don't want to pass in the root, I believe. We want to pass in the node that is in the children. So this kind of same thing. Something like this. So if board, we would call DFS, or we can just use this. So this would be row column root.children row column. So this is column. Okay, so now that we did that, so we're going to append to cur here, so that should be fine. So let's return the res here. And I think that looks fine. We're probably going to have some errors. It's definitely complicated code. So dict is not callable. Okay. Row column root dot children board row column. Interesting. Did I have too many parentheses here? Yes. So this needs to be brackets. And so this does as well, I suppose. Right, so this needs to be brackets because it's like this. This is like this. Let's try that. Okay, so we have an error. So we have oath and oeat. So why do we have oeat? That's a bit strange. But for a second one, it works, but for this one it doesn't. So for some reason, we are appending this O every time. So why is that? Ifs, board, row column. That looks fine. Is our oeat too many times? I think, I see the problem. I see the problem. So we have this return, but we still have to pop regardless. So we still have to pop here because we appended. So let's try that. Okay, let's take a look. Hopefully that's fast enough. We might have to make some optimizations if it's too slow. Like I think there are some optimizations that I remember doing this problem, but let's see. Okay, so wait, okay, so we do have. Okay, so that's another thing. I probably wanted unique. Yeah, so it wanted unique answers. Yeah. And so what we need to do, like let's say this is OA and this is OA and things like that. So we need to have one more data type. Pretty straightforward. So this res can actually be a set. Now we can, where are we adding to the res? Let's take a look. Res.append. So instead of res.append, we can just do res.add. Now we just return res. I think this should work as a list anyway. Let's see, yeah. I think it'll just convert it for us. And let's see if it's too slow, and if it's too slow, we're going to have to make some other modifications to this. It might be too slow, I'm not exactly sure. Because this one, I remember when I did this on LeetCode, it barely passes. So, okay, where's AAA? Output AAA. So what happened here? Okay. So it looks like we are going back and forth, which is a problem. So we're coming here. Yeah, so we're coming here, and then we're coming back. And so we aren't... We probably do need, like, let's see what that would look like, actually, in this code. So let's say we had AA. Okay, let's say we had this AA. And let's try to walk through it. And then we are looking for AAA. Okay, so it's going to go in this A. It'll add it to the cur, so let's just say our cur is A. We're here. Then we are going to go here. And yeah, so then we're adding it. Now we do go here, which is a problem. So we need to have some kind of thing where we can't go back to a node that we were already there. And so we do need to have a visited set, I think, is what we need. Set. And then simply for backtracking, what we need to do is we need to do the same thing here. We need to add the node to our visited set. So therefore, we can't go back and forth. So just visited dot add. And we can just add row column here. Then we can remove here. So remove, I believe. Okay. So visited.add row column, visited.remove row column, and then we also need it here. Okay, so we need one more check, right? So we need, this is going a little out of bounds, but that's okay. So we need new row, new column, not in visited, and this actually needs to be here. I guess we can split this up, so we can just split these up a little bit to make it cleaner code. So if this, then we can have an and here, and there. Okay, so something like that. So let's try to see that. Okay, so we have an error, we have oath, and we expected oath and eat. So I think that means we are... Oh, right, so this should be remove. Okay. Okay. Definitely a lot of stuff for this problem. It's not super easy, and it still might be too slow, so we'll see. Okay, so it passed, which is good. This one sorry, we might cut out for a second. This definitely is a tough problem for sure. There's a lot of room to make errors. And when you make a solution, if you forget one of these optimizations, there might even be more. I think there is actually one more that I'm forgetting. But if you forget any optimizations, I think it's really close to not being able to run on LeetCode. Even, yeah, like when I submitted this, how close was this to? I think this was still not like a top solution, so I think there's another one let's see how many, just to double check again. Yeah, so we're only beating 20%. So it's definitely a close one, and you can have time limit exceeded if you have some issues. So let's think of the time and space complexity. This might get tricky for sure. So time, space. Okay, so what are we doing? We have this directions array, which is negligible. This is negligible. We have a try node for every single letter in every single word. And so that might be our limiting factor, but or actually that's space. So for our try nodes, we actually go through every single letter of every single word. So that's going to be, let's just make up some variables again here. Let's just say W equals word length, right? And N equals word count, let's say. So that part is going to be W times N to go over every single letter of every single word and make these tries. Okay. And then we're going to do this backtracking. So backtracking, you will have repetitive operations. So you will be checking multiple nodes because it matters where you got here from. So for every single node, we can go to every single other node, and then we can go back. But I think that won't be as expensive compared to this making of the tries because these are only 12 by 12. Like they're very small. So I think that part of the code should actually be negligible compared to making these tries. So I think most of the time is going to be spent making these tries if I'm correct. And the average backtracking is pretty much brute force. So it's definitely not an ideal solution, but we do have a visited array, so we can only go from every node to n by m. But like I said, even if you do like n by m by n, it's still 10 times 12 times 12, which is not that big. So I think that part is negligible, and I think our time complexity is going to be mostly towards building this try. You can correct me if I'm wrong, or I might edit this later if I am. But so space. So we are going to make these tries, and these tries can technically, if all the words are completely different and start with completely different letters, then our space is going to be the same thing. It's going to be W times N because we're going to have a try for every single one of these. And then are we making anything else? So we do have a res, which is going to be it could be up to every single word, which would be also W times N. And we have a cur, which is just going to be the length of a word maximum. And we do have a visited set, and we have I think we have one more set. No, this is just a set. So this visited set, though, is basically negligible because the most it can ever be is 10 by 12, so that doesn't matter. So I think the space is this as well. All right, so this was quite a long problem, and I hope you enjoyed it. And if you like these kinds of videos, like and subscribe, and I'm going to continue making more. So thanks for watching.